都因为现在怎么样？那定下专业水平。
We got some friends here.
But it's all like, a lot of it's like audience. Like a lot of structure.
I got it too. It's too
I kind of like to see
Like I get notifications about that, so I like this great and change it, then I'll click
Yeah. That's a new thing, setting up student programs. Usually what happens is presentation.
他教的比较他每一次抽作业不要分了吗？我就不懂是怎么想的。被挂的嘛？我要跟他来上课干嘛？
So you want your sentences to be yeah, use like on my Mac for sure. And then like this. And then like yeah, I kind of just my his office is right around the corner, so we will.
Okay. Hello everybody. I think we should start. So Cyril, we'll spend about 40 minutes or 45 minutes talking about the class, and then the remaining 30 minutes will be used for quiz. And also, because this, during the quiz, most students will show up. So some of you, quite many of you haven't fetched your graded quiz for quiz 1. So after you finish your quiz, you can come to get your first quiz. Okay, so in the last lecture, we extend our simple linear regression to a regression model with multiple explanatory variables. So suppose now we have D explanatory variables, and we want to use those D variables to predict our target variable or dependent variable. So we know that for a simple regression case, simple linear regression case, our regression function is simply written as ax plus b. We assume that this function can represent the target variable value. So if in the two-dimensional space, it's just a line. A is the slope and b is the intercept. So now, how can we extend this one variable case to a D variable case? In other words, how can we represent the linear regression model for D variables? Can anyone remember?
We should use small variable a.
Yeah. Any more supplement?
Isn't it like where you have a vector alpha that multiplies, it's like a weight for every value in x?
Yeah. So think of it. We're also doing review, right? Those kind of things might be covered in the quiz, 40 minutes later, right? So for D variable case, we can simply extend our linear regression model. So right now we have D explanatory variables, right? So it's a function of D variables rather than one variable. And then it's just a simple extension. We know that in a simple regression case, we have one intercept, right? And also one weight for the variable. So now we have a D variables, so we should introduce D extra weights. So we change the notation a little bit, it's just for convenience. So for intercept, we now denote it by alpha 0. And then for the first variable, x1, we introduce its weight alpha 1. So alpha 1, x1. And the second variable, x2, we introduce its weight alpha 2. And we can continue until the dth variable, the last variable. So it's alpha d, xd. So this is our regression function for our target variable y. So we assume our target variable can be expressed as a linear function of those D variables. So this is a general linear regression problem for any number of explanatory variables. Right? So then we introduce how to give a succinct expression of this linear function in terms of matrix and vectors. So what is its succinct representation? An idea? So every time when we look at, okay, this is summation of some pairwise production, we should think of the inner product, right? So we can consider two vectors. One vector consists of all the weights and intercept. So they will be alpha 0, alpha 1 to alpha d. And the second vector is what? 1. Yeah, the first element will be 1, right? Because it is used to account for the intercept. And the second is x1, counterpart of alpha 1. And until xd. So actually our linear regression model, this function, can be expressed as the inner product between the two vectors. We can check for the definition. And then we can define this vector as our parameter vector, alpha vector. Right? And this vector as our input vector, which consists of all the observed variable values, and also augmented with constant 1. Remember, this constant 1 is always used to account for the intercept. So we can simply rewrite this function as an inner product between our alpha vector, alpha arrow, and the input vector, x. And this is the most commonly used representation of linear regression model, because we're going to operate everything in the matrix and the vector world. And then we, in the last lecture, we introduced, by given n training instances, how can we identify the best weight vector, alpha arrow. So one instance will be one pair of like explanatory variables and dependent variable values. So x1 arrow, y1, x2 arrow, y2, until the nth instance will be xn arrow and yn. So again, each specific input vector consists of the constant 1 and also the values for the d explanatory variables. So without loss of generality, let me rewrite it like here. Right? So the first element will be 1, the second will be the value of the x1 observed in ith instance. So a third will be xi2 and continue xid. And this is for all the instance. And then we derive how can we obtain the best parameter vector alpha arrow that fit these n training instances. If you still have some impression or you haven't watched the lecture, it's kind of a tedious procedure. We can take the gradient. So first question is how can we fit the model? What kind of strategy do we fit the model? An idea?
SSE.
Yeah, SSE. Right? So every time when we think of feeding a model to some data, we're going to come out an objective function called SSE. That is the squared sum of the squared error over each instance. So let me write down again. Right? So what is SSE? So SSE will be the summation of the square error over all the instances. Right? So for ith instance, the square error will be yi subtracted by our prediction result. That is here, right? That is here. This is our prediction model. So this is alpha arrow and xi arrow. That i's input vector and take square. This is squared error, and we sum the squared error over all the instance. And then if we want to find out the best alpha vector which fit those n-training instances, we simply take the derivative. We simply minimize this SSE, right? And how to minimize it? We take the derivative over each element in this alpha vector and set the derivative to be 0, right? Because alpha arrow is a d plus 1 dimensional vector. That means we end up with d plus 1 equations. So if we want to minimize SAE, it is equivalent to say, okay, I want to compute the derivative of SSE with respect to each element in this alpha vector and set them to be 0, right? So maybe I should not use alpha I. I should use alpha G. And then it just goes through all the elements in the alpha G, in the alpha vector. So actually, when we set, this is actually a set of equations, d plus 1 equations. And when we want to obtain the best, the optimal alpha vector, we have to solve this d plus 1 equations. And of course, we can do it one by one. But in the last lecture, we spent quite a long time to show you how we express all the left-hand sides of the d plus 1 equations to be a matrix vector operations and also the right-hand side. So we want to repeat this process again. Otherwise, we don't have time to take the quiz. But I hope you have practiced after the class, right? So the left-hand side turns out to be x transpose y, and the right-hand side turns out to be x transpose x times alpha. So here, what is x? What is the input matrix x? Yeah, we stack all the training instances together, we form a input matrix X, right? So in the matrix world, we are given n training instances. You should come out this input matrix immediately, right? So the input matrix is defined as x1 arrow, I suppose. X2 arrow, I suppose, until xn. Xn arrow transpose. So namely, each row corresponds to one input vector, which consists of all the observed variable values and also augmented with 1. So input matrix is simply n times d plus 1. And also, we stack all the values of the target variables into a vector line. So this is y, right? y1, y2, and yn. This is n dimensional column vector. And then we can express this d plus 1 set of equations as actually the matrix equation. So this is a matrix, this is the actual vector, and this is a vector. And then our problem turns out to be solve this matrix equation, which is pretty straightforward. You multiply both sides by the inverse of x transpose x. So you end up with the optimal alpha vector to be x transpose x inverse and multiplying with the left-hand side, which is x transpose y. And this is actually d plus 1 dimensional vector. You can check for that. So actually, this case is general, meaning that even you set d equals to 1, it still holds. So what will be the case for d equals to 1? Yeah, we return to our simple linear regression model with only one variable, right? Then it becomes ax plus b. And you can say this is actually another way to represent our optimal slope and intercept. Right? But this is actually, when d equals to 1, this is a 2 by 1 vector, right? Because d plus 1, this is d plus 1 dimensional vector, right? When d equals to 1, this is a two-dimensional vector, meaning that we have two values. Obviously, the first one corresponds to the intercept, the second one corresponds to the slope, because this is our definition of alpha vector. And you can check the equivalence between this matrix vector representation and what we have derived the class before the last class, the scalar version, and when d is set to 1. That will be interesting comparison. So now, we actually have introduced nearly everything about the linear regression problem. But sometimes you will think linear regression lead to too simplified. You can imagine that in the real world, every dependency relationship can, appropriate to be expressed as a linear function. Obviously, this is not possible, right? The real world is complex. It could be highly nonlinear. So sometimes it might be more useful to incorporate a more complex regression function rather than this simple linear function. Then now, if I want to express our target variable in terms of a nonlinear function of those variables, explanatory variables, then what kind of function form do you have?
Polynomial.
Yeah, polynomial. Any other idea? Yeah, exponential. Other idea?
Cosine, sine, log.
Yeah, cosine, sine, log. Those are all great suggestions, great proposal. Also, neural nets. Neural nets is also a nonlinear function. So, but today we will introduce the polynomial, as you just mentioned. Why? Because this is a simple extension of the linear function, and we will still start with simple linear regression model, meaning that we only have one explanatory variable, and we want to predict one target variable y. So for linear regression model, okay, we know we can express y in terms of x by ax plus b, right? And now for polynomial, how do we express it?
Ax squared plus bx plus c.
Yeah, this is quadratic. Right? We can consider it in a more general case. Right? So actually, regarding polynomial, we should define what? For general polynomial, we should refer what?
The degree.
Yes, excellent. Right? The degree. We should designate the degree for the polynomial you're considering. So consider a p-feld order polynomial. What is this general form for p-feld order polynomial? Can't remember.
Alpha x plus alpha 2x squared plus alpha
Yeah,
3x.
yeah. Exactly, right? So we first write down as a zero order term, meaning that it is just a constant. Right? So we can denote it by alpha 0. This means that this is actually alpha 0 times x to 0. Because when x take the power of 0, then it becomes 1. So it is just constant. And then second term, this alpha 1 x. That means x take the power of 1. Right? And third term is what? What is third term? Yeah, square, right? Alpha 2 x2. And we can continue until pth order term. So these are alpha p xp. So this is a general form of the polynomials, pth order polynomial. Of course, if you specify this is a pth order polynomial, you should ensure that the coefficient alpha p is not 0. Right? Otherwise, it is at most p minus 1 polynomial, p minus 1 order polynomial. So we can consider that actually the linear regression is a specific polynomial regression. Why?
Polynomial degree 1.
Yeah, polynomial degree 1. Right? So if p equals to let me erase this. So if p equals to 0, then what will be the polynomial function d? Yeah, alpha 0. It is constant. It's just constant. And p equals to 1, as we just discussed, it's a line, right? Then it corresponds to our linear regression model. And p equals to 2. What is it? Quadratic function, right? Some of you have just proposed, right, for nonlinear regression. So it could be like this, or it could be like this, whatever. Depends on the coefficient of the second order term, right? And p equals to 3. Could be like this, or like this, whatever. And you can increase p, and you can imagine when p is large, it could be like this. It's some continuous function, but it's nonlinear function. You can see it must be wavy, right? So now we can use a polynomial function to replace the linear regression function to do the nonlinear regression. So namely, we use this pth order polynomial as our regression function. Then we can expect that we can capture some nonlinear relationship between our target variable and those and our explanatory variable x. Right? So the question is, now I'll give you n training instances. How can we identify those parameters? If we specify our polynomial regression function, it has pth order, right? We should identify p plus 1 parameters, alpha 0, alpha 1 to alpha p plus 1 parameters. Then the question would be, how can we find out those best p plus 1 parameters? How can we do that? Any idea? So suppose we have a n training instance. So x1, y1 to xn, yn, right? So now, because this is a simple regression, meaning that x1, x2, x2, xn are just scalars. And then how can we, given our order p polynomial regression, how can we estimate those parameters from n training instances? How can we do that?
Minimize excessively.
Yeah, exactly, right? No matter what kind of regression function or regression model you use, we want to fit data SSE, the most common used objective function. So we can copy the SSE here, right? So in polynomial, it will be a summation, still summation over n instances and yi minus the polynomial xi and take squared. And naively, we can simply take the derivative of the SSE over each coefficient here of I and set them to be 0. So alpha I will be starting from 0 to p, right? And then we solve those p plus 1 equations. We'll end up with our optimal alpha 0, alpha 1 to alpha p. So this is a straightforward idea. And now let us consider whether can we use something we have already in hand to directly solve this problem. Can we? We don't want to do those tedious things again, right? So can we directly use existing formula to finish the optimization procedure?
What's that you wrote before the 0 is less than n is less than p?
Here?
No, sorry, the derivative of the SSE with respect to alpha I.
Yeah, alpha I.
Yeah, equals.
Equal to 0.
That's a 0?
Yeah, that's 0.
Oh,
It doesn't look like a 0. Okay, sorry.
I mean, it kind of looks like a 0. I guess I'm wondering why it's just a 0.
Oh, I want to minimize SSE, right? I want to minimize SSE.
Oh, you're just setting the gradient.
Yeah, set the gradient to be 0. That's the strategy we always use.
Okay.
Okay. So the question is that when I take the derivative, we take the gradient with respect to each of those coefficients set to be 0, we have to solve p plus 1 equations. That's really tedious. So we're wondering whether we can use the previous results to directly address this problem rather than do those manually stuff. Right? How can we do that? We can look back to our polynomial regression function again. Right? So now, from this function form, what can we observe?
It's an inner product between two vectors, the alpha vector, and then like a polynomial vector, I guess you could call it, with a 1 in front of it.
Yeah. Yeah. Excellent answer. So we say, again, that's why I didn't erase the definition for linear regression. So you can see, actually, these two forms is surprisingly similar. Right? So this also represents an inner product. So what is the corresponding two vectors? Yeah, the first one is alpha vector. So similar to this alpha vector, or identical to this alpha vector. So is here clear to you guys at last slide? Okay. So also, all of this polynomial regression, we can come out two vectors. The first is alpha vector, and how about the second vector? What is the second vector?
1x squared.
Yeah, yeah, exactly. Just here, right? 1x squared to xp. 1x squared to xp. Oh, sorry, this is not x. It's alpha p. So it's xp. So both are p plus 1 dimensional vector. And now we actually can rewrite our polynomial regression, p thought of polynomial regression by the inner product between this alpha vector and x vector. X vector is actually some transformation of the original values of the variables. So now we look at we found a similarity between a linear regression model with multiple variables and a polynomial regression model. And then what is the next step? Actually, we have overcome the difficult step, the most difficult step. The remaining things is really straightforward. And what's the next step? Yeah, of course we need to use SSE.
You can just use a solution for the
Yeah, because the form are exactly the same, right? So you can imagine you put the exactly same form into here, you end up with exactly the same form here, right? So the solution must have a, where's the solution? Oh, I erase it. So let me write down this solution, the alpha equals to x transpose x inverse x transpose y. Yeah. So the solution for our polynomial regression must have the same form, right? Then the question would be, how can we identify this input matrix and output vector y? How can we identify it? No question at this point, right? So we know, okay, our polynomial regression model is an inner product, right? And also our linear regression model is an inner product. So their SSE, the two SSE, actually have the same form, meaning that when you solve this, we minimize this SSE, then the optimal solution will have the same form as well, right? The problem is that the definition of this input matrix X and output vector Y could be different, but the form must be the same. Then how can we identify X and Y for pth order polynomial regression here? Any idea?
The input matrix X is just your transformed X vectors transposed and then as with the rows of it.
Right. Very good. So we can say this is actually define our input vector, right? So in the linear regression case, what is our input vector? Here, right? And then we just stack all the input vectors together to obtain our input matrix. Right? The first row is the first input vector, and second row is second input vector. But now in our polynomial regression case, the input vector is simply the transform features. So this is an input vector for the first instance, and then we can stack the second instance, a second input vector for the second instance, third input vector for the third input vector, follow exactly the same way. And what about y? Yeah, y is the same, but it doesn't change. All the values of the observed dependent variables. So that means to solve the pth order polynomial regression, we can simply construct a n times p plus 1 input matrix. So the first row will be the transform features or transform variables for the first instance. We can still denote it by x1 arrow and take transpose because this is a column vector. And the second would be x2 transpose. And until the last one would be xn transpose. And for to clarify it, so for each transform feature, transform variable is written as 1 xi squared until xi p. It corresponds to here. And we know that we should go through all the instances. And also, we have our output vector, which consists of all the values of dependent variables. And now that we have constructed our input matrix and the output vector y, we can directly apply this formula to solve our best polynomial coefficients here, alpha 0, alpha 1, alpha p. So I can simply copy it here if you want to take notes. So the best alpha is apply what we have derived for linear regression model with multiple variables. Exactly the same thing. So this is a polynomial regression.
Does this only work with a single variable?
What?
Does this only work with a single variable?
No, actually you can extend it. That's something I want to discuss actually just after this. Yeah, you mentioned that's good. So that's the current case is only for single variable, right? But what if I want to do the polynomial not only one on x, but only on some extra variable like x2? And then how can we do that? So suppose I use this place. So suppose I have two variables. I have two explanatory variables, and our polynomial regression becomes the p1th order for x1 and p1th order polynomial of x1, p2 orders polynomial of x2. So it will be like alpha 0 x1 plus alpha 1 x1 plus alpha 2 x1 squared plus alpha p1 x1 p1. This is a p1 order polynomial for x1, right? And we can plus an actual polynomial of x2, right? Say beta 0 plus beta 1 x2, beta 2 x2 squared until like beta p2 x2 p2. So now it consists of two variables, right? So the question is that can we use a similar method to obtain the best parameters of those coefficients? Can we? Yeah, it's a straightforward extension. Right? You can still write it as an inner product between a big vector. And here we actually have like a 2p plus 1 parameters here. Right? And here will be 1x, x squared to xp, this x1, right? Then x2, x2 squared, x2 to the 3 to x2 to the p2. Right? So you just expand your input vector, then everything follows. Everything follows. And as long as you construct your input matrix, you can use this formula to solve your optimal parameters.
But does that equation represent a whole quadratic space? Because sometimes maybe we have x1 times x2 times something.
Yeah, that's even more general. Okay. So actually, you can even extend this kind of method from like polynomial to kind of arbitrary nonlinear feature transformation, right? So you can actually write it as a more general form. Maybe it's more clear, right? So now, suppose I don't want to polynomials. It's kind of tedious. So I want to use I want to create like a number of features. So each feature is a function of x1, x2. Right? So it will be alpha phi1, x1, x2, phi2, x1, x2. Until suppose you have p features. So you have a p feature transformation functions. And now you still write it as weighted sum of those p features. So we preserve the alpha 0, and then alpha 1, and the first feature transformation or variable transformation, the second feature transformation, until t is feature transformation. And each feature transformation or variable transformation can be highly nonlinear. You can incorporate anything you just mentioned, like sine, cosine, logarithm, exponential, whatever, into this function. So now you come out a very flexible nonlinear regression model, because those phi 1, phi 2 to phi p can be taken to be any nonlinear function. And then the question would be, how can you estimate those coefficients? And how do you estimate?
It's the same equation.
Yeah, same thing, right? You construct your input vector by what? Now your input vector is changed to here, right? All the feature transformations. And then you still have your alpha vector here, alpha 0 to alpha t. And then you construct your input matrix by stacking all the transformed vector in each row. And then you use the same formula to get your best parameters. So this is a very general way to construct a nonlinear regression model. It is highly nonlinear, but you can simply solve it still by using the solution obtained in linear regression. So there is a very important branch of research called kernel learning method. So basically, we're considering if you can extend your feature transformation. Like you have a p feature transformations, right? So how about if you extend p feature transformation to be like infinite number of feature transformations? Suppose I have an infinite number of nonlinear feature transformations and plug them into this function form, and it can be efficiently or effectively learn the model, namely those alpha 1, alpha 0, alpha 1, alpha 2, alpha p to alpha infinity. How can we do that? This is called kernel learning, because we are going to use some elegant properties of the Hilbert space properties. You can avoid direct computation of linear product. But anyway, this is out of it's not scope of our course. So the last point I want to mention about the linear regression. So remember our linear regression model. Oh, let us just use the function here, right? So in addition to use this function to predict our interested variable, y, right? It can also be very useful to explain data. So you can consider, take x2 as an example. If alpha 2 is very small, like 10 to minus 6, then what does it mean?
It's almost irrelevant.
Yeah, it's almost irrelevant, right? Because the prediction of our target variable has little influence. Is little influenced by x2, right? Because its coefficient is very small. And if the coefficient is very large, say a more extreme case like 10 to 6, then what does it mean? Very strong related, right? Meaning that the value of x2 can directly determine the prediction. So this is very useful for our data mining task. For example, if I want to identify what kind of factors or causes can lead to some particular disease, and I don't know what kind of factors, right? I can collect like 1,000 factors, 1,000 causes. And then what can I do? I can build up a linear regression model by combining all possible factors or causes to predict the disease status. And after we train our linear regression model, we can look into their coefficients or weights of each factor. If some weight is very small, meaning that the corresponding factor has lead to influence in predicting disease status, then you can say, okay, that factor could be irrelevant. We can throw them out. But if those some weights are not small, and it can significantly determine the value of prediction, then that would be very important. And a more advanced algorithm will add some regularizer over those weights or coefficients, such that after your learning procedure, those irrelevant factors, their corresponding weights are directly shrink to 0. This is called sparse learning or feature selection or whatever. It's a very important application and very wide usage. Okay, I think we should start with that.